and I'm here to talk to you today about a new product called NeuraLeap that allows for optical mixing and fast Z focusing on our multi-photon systems. Before I get into that, I want to introduce you to our flagship system, the 2P+, which is our main workhorse for multi-photon imaging and where the NeuraLeap module will be utilized. The 2P+ is really the ultimate two-photon platform, which can service all of your imaging needs in one package. It has a translating base for all of your in vivo or slice experiments, optional substage optics for transmitted fluorescence collection and harmonic imaging, as well as dot device for slice illumination, a rotating nose piece for imaging at different angles, large collection optics for better detection, as well as a large field of view for imaging. It has independent galvos to control photostimulation from 1 or 2P laser sources, as well as LEDs for full field illumination. It's compatible with our holographic stimulation module, the NeuraLight 3D, which uses an SLM, spatial light modulator, to project activation spots in 3 dimensions to your sample. It can incorporate an electrotunable lens for remote focusing uncoupled from objective position, and it has coatings ready for 3P imaging up to 1700 nanometers. And of course, it's going to have a new module that I'm here to talk to you about that arose from the need to image volumes at greater speeds, the NeuraLeap. NeuraLeap was originally developed due to the need to image volumes of tissue with as little added lag as possible. For example, recording neural activity across different layers of cortex, as you can see here. Typically, fast acquisition uses a piezo driver for the objective or an electrotunable lens module for remote focusing. And while these are a good solution for many applications, they are still limited by their switching time. If we look at current options for Z stepping that we offer, the Z motor has a large range, but is rather slow and is good for anatomical work. Piezos have a good range and faster switching speed, but are limited by the fact that the objective moves, making it slower than other options. ETLs are faster than piezos and are uncoupled from the objective, but still have a switching speed that can slow down volume imaging. And that is where NeuraLeap comes in. It increases the speed of volumetric imaging using a combination of methods. The first of which is to simply extend the depth of field. So what I mean by this is that a volume can be imaged more rapidly simply by collecting light from a larger section in Z. We're mostly familiar with the Gaussian beam that we produce in 2P imaging. This produces a small point of activation and is in part why two-photon imaging is so powerful. But it is a double-edged sword, as thin optical sectioning requires taking more Z samples to get data at different depths, thus creating the need for devices like the ETL or the piezo. We can increase depth of field that is imaged by simply underfilling an objective, which produces an elongated depth of field, but it is not significantly larger than what we're typically used to. By illuminating with an annulus, however, we can get a significantly larger depth of field, well over 100 microns. This type of imaging integrates all signals across your depth of field, making it useful for many applications. It is more resilient to motion artifacts, and it allows you to collect volumes at single frame rates if your sample is sparse, or if depth information isn't necessary. It still suffers from this loss of depth information though, as all volume is collected in a single frame. As I said, we are accustomed to imaging with a Gaussian beam and using a Z device to sweep it across different planes. This method of imaging produces separation in Z signals, which is often required in denser lines. But imaging planes can be slow as Z devices typically have to settle before collecting frames. This delay makes imaging many planes costly to temporal resolution, as can be seen here imaging through 80 microns of tissue. By increasing depth of field, we can now image this whole section at the same time, however. In sparse lines, like I've shown here, we can use a larger depth of field to collect this data from 80 microns of the sample being imaged here with depth information applied from the Z-stack previously collected. In cases like the one shown here, you can image this volume at frame rates. If you have an application that requires a smaller spot size, you'll be happy to know that the beam is addressable and can be restricted using a digital micromirror.